Okay, so here's part two to our first day. This slide we already did on the previous day. This slide here is a reminder for how we deal with rational exponents. We've got a power and we've got a root, and it actually does not matter which way we do it. We can do the power first and then the root, or the root first and then the power. I will recommend doing it the second way that we have there, the circled one, because usually when you take a root, the value gets smaller. So then we're dealing with a smaller number raised to an exponent, and that usually makes the work a little bit easier to do. Reminder here, rational powers are not used with negative bases. We won't have negative bases with fractional exponents because then actually this doesn't work. It does matter which way I do it. Whether it's the power first or the root, that could get different answers. So we want to make sure that we're not writing it this way. If we want to talk about the cube root of negative 27, we should be using the radical notation instead. This is okay. That is not okay. What's weird is your calculator will give you a value for this. So you want to make sure you understand that really what your calculator is doing, it's doing this. And that's how you should write it, because that's actually what's going on. All right, here we have some practice now with these rational exponents. We've got the power, which is in the numerator, and we've got the root, which is in the denominator. And then some of them are even going to be negative exponents. So remember, the negative exponent means reciprocal, and it's reciprocal of the base. So it's after I do the fourth root and then the third power, and then I take the reciprocal of whatever that answer it is. That would be the most logical way to probably walk through that one. So as we look at the first one over here, 64 to the 2/3, it means the cube root of 64, and then that answer to the second power. So I'm going to do them in this order as I make the numbers get smaller when I do the root, and then I can take that answer to whatever exponent's being asked, hopefully. So 64 to the 2/3 means the cube root is 64, which is 4. And then 4 squared would be 16. So the answer would be 16. Next one, 25 to the 3/2. It's the square root of 25, which would be 5. And then to the third, 5 to the third would be 125. 16 to the 3/4 is the fourth root of 16, which would be 2. And then 2 to the third would be 8. And then on part D, the only difference here is now I have a negative exponent, negative 3/4. So I still do the fourth root. That's still in the denominator of my exponent. So it's 2. And now I have a negative 3. And then I take 2 to the third, which would be 8. And then it's 8 to the negative 1, which is 1/8. Which makes sense. The only difference between these two is that they should be reciprocals, because here I had a positive exponent, here I had a negative exponent. All right, next one, 1/8 to the 4/3. So that's going to be 1 to the 4/3 and 8 to the 4/3. So 1 to the 4/3, that one is actually pretty easy to do, because any 1 to any power is just going to be 1. So I end up with a 1 on top, and then I have the cube root of 8, and then that answer to the fourth power. So it's 2 to the fourth, which is 1/16. 100 to the negative 3/2. So now I have three things to deal with. I have a root, I have a power, and then I have to take the reciprocal of that answer. So the square root of 100, because I've got this 2 on the bottom, so the square root of 100 is 10. 10 to the negative third. 10 to the third would be 1,000. And 1,000 to the negative 1 is 1/1000. Part G, 27, m to the 6th, n to the 3rd. So now I have to apply this 2/3 to everything that's in the parentheses. I have a product inside here. So my rule is I will apply the exponent to everything that is on the inside. So 27 to the 2/3 means the cube root of 27, and then square that answer. The cube root of 27 is 3. So and then 3 squared. M to the 6th to the 2/3, we're going to multiply these exponents. Remember, this is the same as 6/1 and 3/1. So I get m to the 12 over 3, which sounds a lot like 12 over 3 is 4, and n to the 6 over 3. So I end up with n to the second. And then, of course, we wouldn't leave something with 3 squared. We would call that 9. So my final answer would be 9m to the fourth, n to the second. So that's the rational exponents and how we deal with those. We really have to understand that the root is what's on the bottom of the fraction when I have the exponent, and the power is what's going to be on top. I realize you're at home, so we probably don't have a half sheet in front of us, but if you remember from advanced algebra, we had those half sheets that had the exponents with them. That's how we would have you guys do these. We would have you do these by just using the half sheet, not using the calculator, just being able to look at the half sheet and figure out what to the fourth power is 16, and then that answer to the third power, what is that equal to? So we'll try to find a way that we can actually assess your understanding of that. I'm sure that that'll be coming up. All right, then we have something that's going to deal with the graphs of these rational power functions. So we have all of these functions, y1 through y7, and we can plug those in our calculator depending on what type of calculator you have. You can look at those in color. That's a pretty efficient way to do it. I actually have it in Desmos that we're going to take a look at those. Y1, 2, 3, 4, 5, 6, and 7. So all of those, you see that exponents are a little different. Make sure that you use parentheses when we have those fractional ones. All right, so getting into questions. Why can y sub 1 equals x squared be classified as a rational power? So rational power is x taken to some rational number. So 2 I could write as 2 over 1, and that's one way to think of that is, yes, indeed, it is rational. It's an integer over an integer. What is the power on the y sub 4? Y sub 4 equals x, so that means x to the 1. And again, that would be 1 over 1. And what's happened to the value of the powers as I move from y sub 1 to y sub 7? Well, it's 2 5/3, 3/2, 1 2/3, 3/5, 1/2. So those values are getting smaller. So we end up with a smaller exponent as we go. Numbers bigger than 1 over here, numbers less than 1 over here, and of course y sub 4 we said is going to be equal to with an exponent of 1. All right, it said do not graph until we're asked to, and I think right now we're going to be asked to. So on step 3, we're actually going to graph this. So I'm going to switch to my Desmos screen, and I'm going to graph these one at a time. So here's the setup. I've got my x going from 0 to 2, my y going from 0 to 2, and now I'm just going to click on each graph to take a look at it. So here's my y equals x squared. We're just looking at the first quadrant, a pretty small segment of the first quadrant. Here's my y equals x to the 5/3, the blue one. Y equals x to the 3/2. Y equals x. There's our line, a purple one. Y equals x to the 2/3. Y equals x to the 3/5. And y equals x to the 1/2. All right, so we can see the graphs. We see obviously some points that looks like they have in common. We're going to see if we can answer some questions then back on here to see if we can summarize those. So which of the graphs appear to cup upwards? Mathematically, that's concave up. So the ones that went like this. So that's cup upwards. So those would be our first 3. Y sub 1, Y sub 2, and Y sub 3. It's not as easy for me to write that on there, so I'm just going to say 1, 2, and 3. Those were the equations. You do want to make sure you're paying attention to what the exponents are on that. I have that in front of me, so I don't necessarily need to write it up there. But the cup downwards, those would be 5, 6, and 7. What numerical values for rational powers produce that concave up graph when I'm over at x is greater than 0, so in the first quadrant? What values of the rational power? So the exponents. The exponent was 2 5/3, and 3/2. And then same question, but now the ones that were concave down, what were the exponents? The exponents were 2/3, 3/5, and 1/2. Number 5, what points do all the graphs have in common? Well, they all go through the points 0, 0, and 1, 1. 0 to any power is 0, 1 to any power is 1. That's why. So we're always going to have those 2 points. Which pairs are inverses? How do the graphs support this? So I'm going to flip back to the graphs. Let's take a look at those. So the ones that are inverses, I'll actually leave y equals x on there. These two are inverses. They're reflections over the line y equals x. So y equals x squared and y equals x to the 1/2. Those are inverses. These two are inverses. Y equals x to the 5/3, y equals x to the 3/5. Exact reflections over the line y equals x. And these two are inverses. Y equals x to the 3/2, y equals x to the 2/3. So the ones that are inverses are the ones that have the reciprocal exponents. And how do the graphs support this? They are reflections over the line y equals x. What's true about the powers of these pairs of inverses? The powers are reciprocals. So reciprocal powers are going to be inverses of each other. They will actually undo each other. So we'll take a look at that maybe when we do some solving. All right, so what you're going to be asked is, well, can we make this kind of general when we think about the exponents? What will the graph look like? So this side, the left side here, f of x equals x to the m over n when m is greater than n. So here I'm going to have my positive values, m and n are integers. So are positive integers. M is greater than n. So an example could be maybe one that we just looked at. 3 is greater than 2. So if I have x to the 3 over 2, what is that graph going to look like? So the graph, it's going to go through the point 0, 0, we said that, and it's going to go through the point 1, 1 every time that I have this rational power. So then the question is, how does it go through that? Does it go through just straight through like a line? Does it go through like a parabola? Does it go through like a square root graph? And hopefully we understand that it's going to go through like a parabola. It's going to be concave up as it goes. Got a little shaky there. And the reason is, think about what if I just use the numbers 2 and 1? If I use the m is 2 and n is 1, I would be looking at the graph of x to the 2. Just in that part, and just in that first quadrant, there's our graph of it. All right, what if m is less than n? So if m is less than n, I'm going to pick m is 1 and n is 2. So x to the 1 over 2. Well, what are the 2 points that they have in common? They're going to go through 0, 0. The graphs are going to go through 1, 1. And then how do I go through those 2 points? Straight like a line, parabola, or like a square root graph? Well, this one's going to be more like a square root graph, concave down. And imagine that. What does that look like from way back in our study of different functions? That's the square root graph. Well, that is the square root graph up there. X to the 1/2, that means the square root. So there's our graph. It's going to be concave down. But that's going to be true for all rational exponents where the numerator is less than the denominator. And this shape of the graph is going to be true whenever the denominator is bigger. Whenever the numerator is bigger than the denominator. What is the equation for the inverse of f of x equals x to the m over n? So this goes to the last question off the activity. The inverse, remember that's our notation for inverse, f to the negative 1 of x. The inverse of f of x would have to equal x to the n over m. And those two would actually undo each other. Those two exponents would undo each other. And we would see that we would end up with just x if we did the composition of functions. All right, so a little bit of finding inverse equations and remembering how we do that. So hopefully you remember the first thing we would do is we would switch the x and the y. So remember, this is just a y over here. H of x is the same as y. So I'm going to switch and say x equals y over 4 to the 3rd minus 1. So I switch the x and the y, and then I solve for y. So I'm going to add 1 to both sides. So I have x plus 1 equals y over 4 to the third. Now I have this, what's being taken to the third power by itself. All of that's to the third. So I'm going to take the cube root of that, cube root of this side, cube root of this side. So I get y over 4 equals cube root of x plus 1. And then the last step would be multiply by 4. Multiply by 4. So the inverse of h of x equals 4 times the cube root of x plus 1. All right, so there's undoing the exponent. Over here, we're going to undo a root. So again, we're going to switch the x and the y. I'm going to do it right over the top so I can maybe save some room. That's x now, and this is now y. So my first step is going to be divide by 3. So x over 3 equals the fourth root of y minus 2. Take both sides now to the fourth power. So I get x to the fourth over 3 to the fourth, which would be 81, equals fourth power and fourth root would simplify out, y minus 2. So I'm going to add 2, and I'm going to add 2. So the inverse of g of x equals 2 plus x to the fourth over 81. F of x equals 5x to the 3/4 plus 2. So again, I'm going to switch. I'm going to change color here. Go to blue. So this would end up being x. This is our y in there. So my first step here, I want to get what has the exponent on by itself. So my first step would be subtract 2. So x minus 2 equals 5y to the 3/4. Then I'm going to divide by 5. And then how do I undo a 3/4 exponent? Well, I would undo the root by taking it to the fourth power. I would undo the power by taking the root. But I can do all of that in one step. I can take this side to the 4/3 exponent and this side to the 4/3 exponent. And if I look and see what happens, I have y to the 3/4 to the 4/3. The rule with a power to a power is I multiply. So I get y to the 12 over 12. 12 over 12 is equal to 1, and that's what I wanted over here. I wanted an exponent of 1. So then my inverse of f of x equals, we can just leave it just like that for now, x minus 2 over 5 to the 4/3 power. And now m of x equals 8 to the x. So I dealt with a base of x with a rational exponent. I had an x up here to the third. I had a fourth root. Here, we notice x is in the exponent. So if I switch, I'm going to have x equals 8 to the y. All right, so I'm supposed, there's an inverse, but if I want to write it in terms of y, I'm supposed to solve for y. So right now, y is in the exponent. And I'm not quite sure how to rewrite that one. I can't take the y-th root or something like that. I'm going to have some type of new function. And it's not really new because you did deal with it last year in advanced algebra. So that's where we're headed next. I need to have a way that I can write what is the exponent equal to. So that's where we're going to run into logarithms. All right, so we're going to think a little bit about the graphs first. So let's go to y equals 2 to the x. We're going to think about that graph. And then it says sketch the graph of the inverse. And then what is the equation of the inverse? So for the y equals 2 to the x, I like to do a little table for that. So I'm going to start with a nice and easy ones. 2 to the first power is going to be 2. 2 to the second power is 4. 2 to the third power is going to be 8. And here's a way to even remember, if you forget what a zero exponent is, think about how did I go this way down the table? I multiplied by 2, multiplied by 2, multiplied by 2. So to go this way, I'm going to divide by 2, divide by 2, divide by 2. 2 divided by 2, I get a 1. And then if I divide by 2 again, I get 1 over 2, which really is telling me 2 to the negative 1 is that reciprocal. And then if I divide by 2 again, which is really multiplying by a half, I get 1/4. So I have those ordered pairs that I can now graph on here. So let me do that. I'll do that one in blue. 0, 1, 1, 2, 2, 4, 3, 8. And then at negative 1, I'm at a half. Negative 2, I'm at a quarter. All right, so I'm going to try to do this with my finger the best I can. So the graph is going to do this. And that hopefully is no surprise. There's our exponential growth graph. All right, so what's going to be different here? It says to graph the inverse. So to remember, the inverse is when we switch the x and the y. So when I switch the x and the y, if I have a table, all I need to do is switch the x and the y. So 1/4 goes to negative 2. 1/2, half goes to negative 1. 1 goes to 0. 2 goes to 1. 4 goes to 2. 8 goes to 3. So now I'm going to graph those. I'll start over here. 8 goes to 3. 4 goes to 2. 2 goes to 1. 1 is at 0. I go over a half, I go down 1. I go over a quarter, I go down 2. And I'm going to try to do this with my finger the best I can. And there's the inverse. And we should not be surprised by that. The inverse looks pretty good. If I think about that inverse, it should be going and being a reflection over the line y equals x, and that looks like a pretty good reflection over the line y equals x when I look at those two graphs. What is the equation of the inverse? So the equation of the inverse, the red one, is going to be x equals 2 to the y. We switch the x and the y. Now what if I wanted to check that in my calculator? There is no x equals, I need this to be y equals. So the y equals is where we're going to run into logarithms. So our definition of a logarithm, if x equals 2 to the y, then y equals log base 2 of x. Y equals log base 2 of x. Here's the base, it's 2. The exponent is what it equals, and the x, the argument, is what happens when I do 2 to the y. So 2 to the y equals x, base, exponent, and then here's the answer. So I'm going to go back to this, y equals log base 2 of x. So 2 is in a subscript position. Everything else would be like on the straight line, the log and the x's and the y. All right, log base 2 of x is the exponent on 2 that gives x. So the answer to a logarithm is an exponent. So when I'm asked what is log base 2 of some number, I'm trying to figure out what is the exponent. So log base 2 of 8 means 2 to what power is 8? So we think of that as 3. We're just doing this rewriting. Base, exponent, answer. Base, exponent, answer. So here we're looking for what's the exponent. 5 to the what equals 25. So that answer is 2. There's the exponent. All right, so base, exponent, answer, log. Here's the base, there's the answer, there's the exponent. So if we just run through these, this is asking log base 3 of 9. So 3 to the what is 9? That's what we're thinking. We should end up with a 2. 3 to the question mark equals 9. Sometimes people put x's in there. There isn't really an x in this expression. It just says log base 3 of 9. So I just write 3 to the question mark equals 9. 7 to the what equals 1. Well, how do I get a 1? When I what exponent do I need that would make it equal to 1? And that's an exponent of 0. 2 to the what is 32? Log base 2 of 32. That answer would be 5. Here's where we get maybe some confusion. Log base 25 of 5. So remember, this is the base, 25 in this case. So 25 to the what equals 5. So what kind of exponent is going to make this get smaller? So the smaller, 25 to the 1/2, is going to be 5 because that 1/2 exponent means square root. So the square root of 25 is going to equal 5. Log base 10 of 100. 10 to what equals 100? That answer would just be 2. So again, this was 2 to the what equals 32. This is 10 to the what equals 100. This one, 10 to the what equals 0.01. Whenever I have a decimal like that, I would encourage you to write that as a fraction because I think it's going to be easier to think about what type of number I need. So this would be 1/10. This is 1/100th. So what do I need for my question mark? I need a reciprocal. So what kind of exponent means reciprocal? It's going to be a negative. But I don't just want a -1 because that would be 1/10. I also need to square it. So the answer to that is going to be -2. These last two, bases of 10, they are pretty common as we go through different log expressions. And we'll see that. That's actually called a common log. So if I do not see a base on there, that's telling me that it is base 10. So maybe as we're just starting, if you don't see the base and it's log, log, just put the 10 in there, and that might be helpful to you. So log 1, log base 10 of 1, 10 to the what equals 1? That answer would be 0. 10 to the what would be 100? That would be 2. 10 to the what would be 10,000? And here we can count the zeros. This works here as well. Count the zeros, count the zeros. It even works up on this one. There aren't any, so it's a 0. It actually even works on this one. As long as you write 0.01, you can even count the zeros, and you have to realize that it would be negative back on that one. All right. Sometimes, well, actually, there is a log button on your calculator, and if you notice it is just log. There's not a base on there. So if you type in log 100, you're going to get the answer too. So it is already programmed in there to be the common log of base 10. So you can check that on your own calculator at home as well. Between what two integers are the following logarithms? So this idea is 3 to some power is not exactly equal to 50. So we had all nice exact answers for over here. We don't have a nice exact answer for this one. So the thought is, how can you tell me, just to be able to have some number sense, what type of answer this should equal? Well, we could make a little list. So 3 to the 1 is 3, 3 to the 2 is 9, 3 to the 3 is 27, 3 to the 4th is 81. So if I want log base 3 of 50, that's telling me that I have an exponent that's going to be between 3 and 4. Because 3 to the 3rd is 27 and 3 to the 4th is 81. Log 600. So there's no base number written, so that's base 10. So 10 to the 1 is 10, 10 to the 2 is 100, 10 to the 3 is 1,000. So this one must be between 2 and 3. All right, that's it. Hopefully now you should be able to get started on Chapter 9, Day 1 worksheet.